What's up, mathematicians? Welcome back to our lesson on area, an introduction to area. At this point, we know how to find the areas of rectangles, triangles, and parallelograms. A natural next question would be, how about finding the area of a general quadrilateral? How can we do that? Now, it turns out the ancient Egyptians had an answer for this question as well. And let's talk a little bit about where that comes from. So, the ancient Egyptians wanted to be able to measure land for several reasons. And in fact, if we think about the word geometry, geometry, geo means land, metry means measurement. So geometry, if you think about the etymology, just means land measurement. And that probably comes from the Egyptians, the fact that the Egyptians cared a lot about measuring land. And a couple reasons that I'll mention for that are, number one, the Nile River would flood its banks every year, which was great because it spread fertile land out, along the valley, which helped the Egyptians grow crops. But it also meant that it could, erode away the property lines, right? The boundaries for marking the different properties. So once the floods receded, they had to redraw the property lines for the farmers, so they knew what land was theirs and could be farmed and what land belonged to the next person over. Connected with that, they also wanted to be able to tax the farmers based on the amount of land they had. And in order to charge the correct amount of tax, they needed to be able to measure the land. Now, one thing that happens when you get into measuring plots of land is you find out that quadrilaterals show up all the time, right? So here's a couple of maps. I don't even know where these are from. I just found them on the internet. But these are parcel maps of, I don't know, some neighborhoods or subdivisions somewhere. And you'll notice that there are a lot of quadrilaterals here. That's just something that naturally happens. When you divide land up into parcels for different people, for different uses, you end up with lots of quadrilaterals. Now, it's not the case that all of the parcels here are quadrilaterals, but most of them are, or at least very closely approximate quadrilaterals. So in order to tax people based on the amount of land they have, it's really useful to be able to measure quadrilaterals, find out what the area of a quadrilateral is. So there are geometric reasons for why all these quadrilaterals show up that we're not going to get into in this video, but the key point to take away is we would like to be able to find the area of general quadrilaterals. The formula that the Egyptians gave us for finding the area of a general quadrilateral is this one right here. Okay, and so here's the general quadrilateral. It has the sides of length A, B, C, and D. And we see the formula up here is saying take the lengths of A and B, add them together and divide by 2. Then take B and D, add them together and divide by 2. Basically what that means is you're taking the average of A and C, and then you're taking the average of B and D. Once you've taken those two averages, you multiply the two averages together, and that is supposed to give you the area of the general quadrilateral. That was their formula. Where did they get that formula? Who knows? I honestly have no idea. But let's try it out. All right, here's my general quadrilateral. This is the formula here, and what I'm going to do is I'm going to take this plus this, take half of it, then this plus this, take half of it, and then take the product of those two averages. Before doing that, of course, I'm going to need to measure the lengths of all four sides. I'll do that now in centimeters. Okay, so I've measured the four sides to the nearest tenth of a centimeter, and now I'm ready to do my calculations. So first I'm going to take these two sides right here. So let's see, 7.7 plus 12.1. I'm going to divide that by 2. I'll plug this in my calculator. 7.7 plus 12.1. And then divide the answer by 2. I get 9.9. 9.9. Now I'll take the average of these two sides. So 6.5 plus 3.7 divide by 2, and again I'll use the calculator to figure that out. And let's see, 6.5 plus 3.7, and I'll divide that answer by 2, and I get 5.1. 5.1. All right, so what this formula is telling me is that if I take the average of these two sides and then the average of these two sides, I can multiply those two averages to get the area. So let's do that next. We'll multiply 9.9 times 5.1, and this gives me 50.49. So the area is equal to 50. I'll just round to the nearest square centimeter. So 50.5 centimeters squared. Because we're dealing with area, it's square centimeters instead of just centimeters. Okay, so according to the Egyptian formula, this is the area of this quadrilateral. Okay, but the thing is, as I look at this answer and I look at this formula and I look at this shape, a question that comes to my mind is, how do I know it's correct, right? This formula, I don't know where it came from. How could we check to determine whether this formula gave us the correct area for this quadrilateral, this sort of imaginary plot of land? Well, one thing we could do is we could divide this quadrilateral into two triangles, and we could find the areas of the two triangles. So let's actually do that and see how close the answer is if it seems like this formula did in fact give us the correct answer. All right, so I'm going to go ahead and draw that. Now that through there to make this two triangles. Now in order to measure these, I'm going to need to know not just the bases, but the heights of these two triangles. So I'll use my square here, my right angle on this triangle, to draw in the heights right there. So that's the height of the thinner triangle here. And now let's go to this triangle. And I'll go ahead and draw in the height of that triangle. Okay, so there we go. Now I'm going to go ahead and measure these heights and this base. Okay, so I've taken my measurements. I have that the base of both triangles is this diagonal here, this length 10.5. And the height of the thinner triangle is 1.9 centimeters. The height of this triangle here is 6.5 centimeters. Now I know that's the same as this length right here, but when you're rounding to the nearest millimeter, that's just what you get. These two lengths are just very close to each other. Now I can use the formula for the area of a triangle to find the areas of these two triangles and add them up. So we know that the area of a triangle is 1/2 base times height. So I'll do the larger triangle first. So 1/2 times the base, 10.5 times the height, which is 6.5. And if I plug that in my calculator, I'm going to get, let's see, 0.5 times 10.5 times 6.5. So I get 34.1 if I round to the nearest square centimeter. Let's write that here. 34.1. Now let's go ahead and do the other triangle. So 1/2 base times height again. Once again, the base is the same. It's that length 10.5, but the height is different. So now the height of this triangle is 1.9. And now let's plug those numbers in the calculator. So 1/2 times 10.5 times 1.9, and I get 9.9. So actually, if I round this to the nearest tenth, I'm going to get 10 exactly. All right, so 10.0. Now if I add these two together, well, 34.1 plus 10 is 44.1 square centimeters. But what do we notice here? We got 44.1 square centimeters using this method, and we got 50.5 square centimeters using this method. These answers are quite a bit different. More than, we can't just chalk this up to like a rounding error. This is a difference. It's over 10% difference. And so what does that mean? I mean, it must be the case then that one of these two answers is just wrong. So is this formula even correct? Maybe it isn't. And it turns out, yeah, this formula is wrong. This is not the correct formula for finding the area of a general quadrilateral, which sort of begs the question, were these ancient Egyptian mathematicians that were calculating the areas of these plots of land, were they bad at math? Were they dumb? Or were they swindlers? Were they cheating those farmers? Which actually, maybe before we think about that, we need to figure out who's at the advantage, like who is better off by using this formula instead of a correct formula. Does this formula give the benefit, the advantage to the farmer, or does it give the advantage to the tax collector, the government? I mean, I'll let you take a guess on that one. Probably wouldn't be too hard to guess. But I'll include that as a homework problem, practice problem, to think about whose advantage is using this incorrect formula too. But we have a bigger question that we really should consider here. So the bigger question, in my opinion, is this. Are we standing on shaky ground here, right? I mean, the ancient Egyptians were wrong about the area of the quadrilateral, the formula they had for it. And maybe they knew that, and maybe they didn't, right? This could be willful ignorance. But consider this, we based our demonstration that their formula was wrong on the formula for the area of a triangle, which we got from, among other places, the Egyptians. Maybe that formula is wrong too. I mean, how do we know that any of our methods for finding area or any of the measurement techniques, proportionality, trigonometry, how do we know any of these things are actually correct, right? I mean, what we're doing as we've gone through it, it makes sense intuitively, logically, whatever that means. It makes sense, but maybe it's just close enough, right? Maybe we just can't tell if our calculations are off. If so, can we think about how we could sort of push our results, our methods, to see if they really hold up? Make them bigger, measure more precisely somehow, verify them in some purely mathematical way? So in lesson 10, we'll look at one way that we can sort of push our approach to finding the area of a rectangle, to try to get a sense for how reliable it is. But we also need to think about those assumptions, right? And I'm not going to go through them again here. I did that in the last video. But we need to take a closer look at those and think about, how do we know all of those assumptions we've been making are correct? So we'll go ahead and sort of wrap this lesson up here, just sort of, maybe we'll just sweep that under the rug. And no, I'm just kidding. We'll definitely take a close look, and we're not just going to sweep it under the rug and forget about it, right? This is a serious geometry class where we want real answers. But we are going to go ahead and wrap this lesson up here and sort of leave those questions hanging in the air. We will revisit them. So in the next lesson, we will take a quick look at measuring circles. And in the following lesson, lesson 10, we will revisit these questions again about how reliable the assumptions we're making actually are. So as always, thank you so much for watching. If you learned something today, please do like and subscribe, and we'll see you in the next video. Bye-bye.